Hi guys. So today what we're going to do is review a lot of the vocabulary that you guys learned in Algebra 2 and a lot of the features and characteristics that you found on graphs. So we're going to look at things like domain and range and end behavior, a lot of things that you looked at throughout the year last year in Algebra 2. So we're going to start with domain and range, which is the one you've been doing for the longest. We are going to use primarily interval notation, which is the parentheses and the brackets. So we talked about this briefly last class. So if you remember, parentheses are for the open circles. It means you get really close to the point but don't actually touch it, whereas the square brackets mean you actually touch the point. Domain, we look at our graph from left to right. So on this first one, the farthest left that we go is -3. It actually touches that point, so it gets a square bracket. The farthest right that we go is 5. It doesn't touch that point. It's an open circle, so it gets a parenthesis. Then we look at range. So for range, we look at bottom to top, and it's very important we go bottom to top because we're going from the smallest number to the biggest number. So the bottom number for range is -1. That's the lowest y value. It actually touches that point, so it gets a square bracket. Then we keep going to the top. The highest that we go is 3. It actually touches that point, so it gets a square bracket. All right, let's look at the next one. Those do have arrows at the end, if you can't tell. So since the graph has arrows, the farthest left that this graph is going to go, it goes forever. So -infinity. The farthest right this graph goes is infinity. Then let's look at range. And again, we go bottom to top. This is one that's really flipped a lot. The lowest y value here is -infinity. The highest y value that we get to is 3. It actually touches 3, so it's a square bracket. All right, and C is actually a little tricky. That does have arrows on the end. So let's look left to right. Well, to the left, this graph is going to keep going all the way to the left. So -infinity is the farthest left. Then this graph keeps going until this point. At that point, it stops. So at -4, my graph stops. It touches that point, so it gets a square bracket. But then my graph picks back up. And if you remember, the way we show that is we use a U for union. The graph picks back up when x is 3. And again, we're listing x's for the domain. And then it keeps going until infinity. Range for this one's also a little tricky, because if you look at this graph and think about what it's doing, this graph over here on the left, it's going to keep going for forever all the way down there. This graph is going to keep going for forever all the way up there, which means that this graph actually has a range of -infinity to infinity. All right, so that's our domain and range. Hopefully that one you remember a little bit because you probably used that one a lot last year. There's just a couple little notes about what we just talked about. What we're also going to look at for domain, though, is how to find the domain without graphing and without just by knowing what the function is. So in order to do these, what we need to figure out is algebraically things we can't do. So for example, you cannot take the square root of a negative number. Okay, we don't know the square root of -3. It's imaginary. So since we know the square root cannot be negative, the way we would work this out is we take whatever is under the square root and we make it greater than or equal to 0. And then we just solve the inequality. Now I'm now going to write that in interval notation. So if x is greater than or equal to 8, that means 8 is the smallest x value. It's or equal to, so it touches, and it keeps going to infinity. The other thing algebraically we cannot do, we cannot divide by 0. So if we cannot divide by 0, that means whatever is on the bottom cannot equal 0, which means that x is not equal to 7. So if x does not equal 7, x can equal everything but 7. So what that will look like, that means we'll start at -infinity and we'll go everywhere until we get to 7. It doesn't touch 7, so we put a parenthesis. Then we do a union, and then we do another parenthesis, because it gets really close to 7 but doesn't touch it. And then it keeps going all the way to infinity. So that would be our domain. And if you remember when you did rational functions in Algebra 2, again, I know it's been a while, this happened because you had a vertical asymptote. Now, I will tell you, A and B are the two most common ones of these that you really need to understand. C, we'll touch back on that one here in a little bit. This is, again, just a little bit of review from last year. Another rule is that you cannot have the argument of a log be 0 or negative. So what you would do, similar to the first question, you take whatever's in the parentheses after log and you make it greater than 0. So x has to be greater than -5. So what makes this different from the first one was possible to be 0. So on the square root, you could do an or equal to. Whereas on this one, there's no or equal to, it's just greater. So again here, A and B are really a little bit more important right now. C we'll come back to later on this year. All right, so some other vocab you did in Algebra 2 was end behavior. Okay, so for end behavior, we had two statements. As x approaches negative infinity, f of x does something. And as x approaches positive infinity, f of x does something. So let's start with the first one. As x approaches negative infinity. Well, that is the left side of my graph. So looking at this first one, the left side of my graph is going up. So as x approaches negative infinity, f of x approaches positive infinity. All right, then let's look at the right side. Okay, so the right side, as x approaches positive infinity, your graph is going down on the right side. So it's approaching, the y's are approaching negative infinity. All right, let's look at the next one. As x approaches negative infinity, okay, so that's the left side. So let's look at the left side of my graph. This one's a little different, okay? This is an exponential function, but if you notice, as your x's are getting smaller and smaller, those y's aren't really going up or down. They're actually going really close to that dotted line. That dotted line is called a horizontal asymptote, and the value of that line, it's at the line of 1. So as my x's get smaller and smaller and smaller, they're going to keep getting closer and closer and closer to that horizontal line at 1. The right side, though, that's a little easier. Okay, that right side, that's getting bigger and bigger and bigger. So the right side is going up towards positive infinity. All right, so again, as x approaches negative infinity, that's the left side of my graph. As x approaches positive infinity, that's the right of our graph. All right, and let's look at this next one. This is an example of a rational function. Again, something you saw in Algebra 2. I know it's been a while. Just trying to throw in some refreshers while we may have them. And put those little arrows there. All right, as x approaches negative infinity, so that's the left side of my graph. Okay, so the left, far left side of this graph. So as this left side gets smaller and smaller and smaller, the y's are getting closer again to the dotted line, to the horizontal asymptote. And on this graph, the horizontal asymptote is at 2. All right, then let's look at the right side. So the right side is also getting closer and closer and closer to that horizontal asymptote, which has a value at 2. When it comes to end behavior, we don't need to worry about that part. That's not the ends, okay? So end behavior, we're looking at the far left arrow and the far right arrow and seeing what they're doing. A lot of times that's going to be positive or negative infinity unless there is a horizontal asymptote that you see. So this B and C example are those special cases where there's not one. But most of what you did last year, you saw a lot of instances where you had arrows like these. All right, so now we're going to talk about mins and maxes. All right, so now if you were in honors Algebra 2 last year, you talked about local or relative mins or maxes. If you were in on level, you might not have talked about those and you only did global or absolute. And that's okay, they're not that hard to figure out. A local or a relative min or max is not necessarily the highest point on the entire graph. It's the highest point relative to the points around it. So what that means, I'm going to highlight a couple points on this first graph. So look at that point right there, okay? It's the top of a curve. It's where your graph kind of turns. So that point, it's not the highest point in the entire graph, but it's the highest point relative to the points around it. So what that point is a relative maximum. It also could be called a local maximum. Those two words are used interchangeably. Okay, so that is a relative maximum. It's not the overall highest point, but it's the highest point in that area. All right, now let's look at another point, this point down here. That point would be, it's the lowest point of the points closest to it. All right, it's the bottom of a curve, but it's not the lowest point in the entire graph. So that is a relative minimum. And then finally, this last point over here, it's actually a little special. It's both things, okay? So this is still a relative minimum, okay? It is the lowest point relative to the points around it, but that point is also the absolute lowest point on the entire graph. So that graph is also an absolute or global minimum. All right, now let's look at the second one, all right? And then it's hard to get arrows on these graphs, sorry guys. So on this one, all right, let's look at this point up here. All right, that point, it's the top of a curve. Okay, it is not the highest point on the whole graph. That is a relative maximum. All right, let's look at this point down here. Bottom of a curve, not the lowest point in the whole graph though, so it's a relative minimum. Now, one special part about this graph, this little curve here in the middle, sometimes people think that that's a min or a max. That's not. It actually has a special name called a point of inflection. But that point actually, not a relative min or max. It's not a min or a max. It doesn't change, increasing, decreasing. We don't need to label it as anything. This graph as well does not have any global min or maxes because it continues to infinity in both directions. All right, so what you're going to do now is you're going to use a calculator to graph these and find any of those extrema that we just did. So what extrema means? That just means any absolute or relative minimums or maximums. Now, the calculator that I usually use, I can't use on my computer anymore. They've changed the software, so I'm going to have to do a separate video for that using the iPad. So I'll come back to those to show you how to graph these on the calculator in order to find those values. All right, now let's talk increasing and decreasing. Okay, so this is another one. If you were in honors last year, you probably did this. If you were in on level, you did not. So what we talk about when a graph is increasing, okay, that means as we look left to right, if the y values get bigger, then the graph is increasing. As we look left to right, if the y values get smaller, the graph is decreasing. So on this first graph, I'm just going to highlight the areas that are increasing. So this graph is increasing on this section and this section. So left to right, the y's get bigger. It also looks like a positive slope. All right, then let's look at where my graph is decreasing. That would be that section right there. Now, when we list intervals, okay, intervals means we list the x values. So we're listing the x values where this is happening. So to list the increasing intervals, okay, the farthest left x value there is -1, and then it keeps increasing until 1. Then it stops and it picks back up, so we're going to use a U for union. It picks back up at 3, and then it keeps going to 5. All right, decreasing, okay, the purple section, again, we're listing the x values where that's happening. So at 1, and then until 3. That's where it's decreasing. Constant we'll see on the next graph. All right, domain and range, if you remember that, try that one on your own real quick. Okay, so domain, left to right, the farthest left x is -1, the farthest right x is 5. It touches both those points with a closed circle, so we use a bracket. Range, bottom to top. The lowest y value is -2. The highest y value is +2. And again, we use brackets because it touches both of those values. All right, let's look at the next graph. So the first thing, just try to identify where the graph is increasing and where the graph is decreasing. So I'll go ahead and label it. It's increasing where I marked green. It's decreasing where I marked purple. Now, where I'm going to highlight here in blue, it's neither increasing or decreasing. That's when it's constant. Okay, so it's staying the same height throughout it. All right, now again, we're going to list the intervals by listing the x values where that's happening. So on that first one, the farthest left x value is -6. Then it keeps going until -2, and that's the only interval where it's increasing. Decreasing, okay, so the x value where it starts is -2. then it keeps going until 2. Constant, it starts at the x value of 2, and then it keeps going until 6. Now, with parentheses and brackets on these increasing and decreasing levels, you can go ahead and use parentheses for those in this class for all of them, okay? The parentheses and the brackets are going to be more important for domain and range. There's 2 different definitions you can use, and depending on what class you're in, it may look a little different. So don't stress about parenthesis versus bracket for increasing and decreasing. Make sure you focus on it for domain and range. All right, so again, domain on this one, the farthest left is -6. It keeps going until the x value of 6. Range, the lowest y value is -7. The highest y value is 3. They get brackets because it touches both of those points. All right, so now again, we're just going to talk about some more vocab on the graph. This is something you've hopefully been seeing since Algebra 1. So it tells me to evaluate f of -2. And we talked about this a little bit last class. So that means when x is -2, what's y? Well, let's look at our graph. When x is -2, the y value is 4. All right, f of 0. When x is 0, y is 0. All right, when x is 1, now this one's a little tricky. There's 2 circles there, but we're going to use the filled in circle. So the filled in circle is 1. And then same thing here, f of 2. The filled in circle is what it actually is, so the filled in circle is 3. Now on the other side of that, it says to find the values where f of x equals 1. So that means to list the x's when y equals 1. So I'm going to draw y equals 1. And there are 2 places where that graph touches, -1 and +1. All right, and then the last one, the average rate of change on the interval -2, 0. This is a really easy question to do, but the vocab kind of throws some people off sometimes. So average rate of change on the interval -2 to 0. So -2 to 0 means from this x until this x, okay? So those are 2 different x values. That's not a coordinate. So it's saying from the x value of -2 until the x value of 0. What is the slope between those 2 points? So rise over run. First of all, it's negative, and I'm going up 1, 2, 3, 4, and over 2. So the average rate of change on that interval is -2. All right, the last one. Now this one is actually going to be new for on-level and potentially honors. I think in honors we just touched it briefly, but even and odd functions. Now, I know in both classes you talked about an even and odd degree. This is different. If a function is even, what that means algebraically is that f of -x is equal to f of x, okay, which might sound confusing. So what that means is if a function is even, let's say the point -1, 2 is on the graph. Well, if -1, 2 is on the graph, then +1, 2 is also on the graph. If the point 7, -5 is on the graph, then -7 looks like a 3. Sorry. Then -7, -5 is also on the graph. That's what's true for even functions. What that means is if a function is even, it has what's called y-axis symmetry. So think about a quadratic, okay? The quadratic parent function is even. If you were to draw a line on the y-axis, that graph would have symmetry. So looking at all these functions that are on here, I'll tell you right now, 2 of them have y-axis symmetry. Sorry about that, guys. Bell lunches. So B has y-axis symmetry. If you were to draw a dotted line there, it's the same graph. That means that function is even. The other function here that's even would be E, because if you drew that dotted line, it has y-axis symmetry. Odd functions look a little different, okay? Algebraically, if f of -x equals -f of x, it has origin symmetry. Now again, that might sound kind of confusing. Algebraically, what that means, if you have the point -1, 2, then what you would get if you had negative 1, 2, if you were to have the point 1, it would go through negative 2 as well. So this one has what's called origin symmetry. So an example of a graph with origin symmetry would be A, okay? This is an example of an odd function. So what that looks like, if it has origin symmetry, it's kind of like you take this graph and you flip it over the x-axis, but then you also flip it over, sorry, I said x-axis. You flip it over the y-axis, then you also flip it over the x-axis. So you essentially flip it twice and you end up with the same graph. That's what origin symmetry is going to look like. All right, so there's one more graph on here that is origin symmetry, and that would be D. So if I took this portion of my graph and I'm going to flip it over both axes. So if I flip it over the y-axis and then I flip it over the x-axis, then I end up in the same place. So that is an example of origin symmetry. So that is an odd function. Now, because we're talking about functions and not degrees, your graph does not have to be either one of these. It's actually more common for functions to be neither. Okay, it's kind of a special case when it is one of these. So a lot of graphs don't have any symmetry at all. So for example, C, that one has neither. So not every one of these is going to have symmetry. All right, so the last thing on there, it says to know your parent functions, all of them, really, really, really well. Now, you do not need to know this for your quiz yet, but this is going to come up in what we do next class a lot. So if you remember, you want to review your parent functions from Algebra 2 a little bit, that'll help you get a head start on next class. It will not be on your first quiz, but again, a little bit of a head start for next class.